And in chapter 1, section 2, we are going to be checking out transformations. And Sophia, I will write bigger, and if you would like, you are more than welcome to move your desk or sit at the table on the other side if you would like to, and scoot it up as close as you want if you need. Because I'll try to write bigger, but I will inevitably forget, and I'm sorry for that. Is it showing up there? Okay, yep, let me move this big whiteboard for you. So you have a, are you cool if I keep the whiteboard and you can just write on it? Okay, yep, and you can swing that chair to the other side. Okay, we're going to be talking about transformations of functions. Now, as we look at these, what we're going to think about with these guys is how does it work in general? So we're going to see it work with linear functions, with quadratics, with square roots. We're going to see this in a bunch of different contexts, but we are going to talk about just some function stuff to get us started. So here we go, functions. Henning, you all right? Okay. Functions and graphs. Now, as we go through this stuff, a lot of this, I'm kind of assuming that you recall from algebra, but I'm also aware that you haven't seen algebra stuff for like 2 years. So please don't hesitate if there's a part that you're unsure of or that maybe you don't recall, please let me know right then and there. Right off the bat, we're going to start with a little definition in here. What's a function? And we might have already defined this the other day, but even if we did, it's good to have it again. What is a function? So we're going to try this. Talk with your neighbors like 30 seconds. I'm going to call on one random person. What's a function? What do you think a function is? So it could cross. I don't know that it has to, but it could cross for sure, like the graph of it. Yeah, it could cross the axes, definitely. So here's something that could cross the axes, definitely. If we have a function, how do we get a representation of it in a picture? Yeah, it could be a line. Does it have to be a line, though? It could be a straight line, yeah? That's a linear function. It could be a parabola. It could be these crazy curved things. Regardless, we're going to say that at its most basic, what a function is it's just a relationship. And prime, you might have the formal definition here. I'm going to veer away from it a little bit. But we're going to say it's a relationship between two variables. And I'm just going to go with the standards here. We have, I'm going to use a semicolon. X is what we consider our independent or our input variable. X equals independent. Or what we call our, lost my train of thought there. I'm cool with independent. We'll say input is another way we can think about that independent variable. We pick what we put in. And then for every function that we deal with, assuming it's in the regular variables, we put in the independent x and it spits out the what? A little bit louder there, Prime. One more, I'm sorry, it's dependent, love it. And it's just because we're facing different directions. Okay, we have the dependent variable, which is going to be our y typically. Dependent. And another way to think about the dependent variable is the output. And there are going to be times where it's easy to get these two mixed up, but there's, for every time that it's easy to get them goofed up, we'll see another example where it's not at all hard. If I take something off the stove, is the temperature a function of time, or is time a function of the temperature? Does the amount of time determine the temperature of the stuff that I took off the stove, or does the temperature of the stuff off the stove determine how much time has passed? Which one impacts the other? Time, right? Time dictates what that temperature is. Certainly the temperature doesn't change how time moves. So that's our independent and dependent. How do we write these functions or denote them? The notation we use. Normally in Algebra 1, when you start talking about function stuff, you'll use y equals. And then that gets pretty cumbersome, especially if we want to have multiple graphs on one Cartesian plane. How on earth do we say that, hey, look at this thing that's a function and its independent variable is x? Ooh, somebody said it. It's a grade you don't want, I assume. F. F what? f of x. Now, for this, again, you never have to write everything that I do. I'm just going to make sure. I don't want to hear f parentheses x. I want to hear f of x when we say this. Now, very specifically, when we're looking at these, the name of the function is this f. That's the name. What is this x telling us? Love it, the independent variable. So I'm just going to say vars, or the variable var. And the reason that I do this is on your calculators, there's a button that says var that stands for variable. So we have our function f, and we use the variable or our input x. Okay. Now, as we're looking at these, do you guys remember ever graphing functions? Okay, little bits, I imagine. F of x equals 2x plus 3. That's a type of thing that we've graphed. Right now, we're going to learn a bit more in our calculators, though. Do you all have your calculators today? All right, let's grab our calculators. We're going to check something out here. I'll grab mine, and I'll get the document camera up and running. Sophia, do you have your calculator? And if you don't, I have a spare, but if you have yours, that'll work too. Okay. All right. Now, on our calculators, when we're graphing things, we can graph a ton of different stuff, and we'll bounce back and forth between these. Historically, like last year in geometry, I used Desmos a lot, which I don't have anything against Desmos, but I want you guys to start learning how to do these. So here's this wonderful calculator. We need to decide what function we're going to graph. And I want to mess with one that's a little bit more interesting than just a straight line. So let's go to, on the very top left of your calculator, there's a y equals button. There might be stuff written there. There might not be. If there is stuff written there, like mine, I'm just going to hit this clear button right here. Okay. So again, if you are a little behind, y equals top left, and then if there's something written here, I'll just hit clear. So let's start with a really nice basic function. And let's say we have x squared. Now, for the squared, just so we can get some tips and tricks here, there's two ways to get square. The way that I do it just naturally is a slow way. I can hit this caret button right here. It's the little up arrow, and it pushes me up into the exponent. And then I can just select 2. Now, what's frustrating about this is if I had like plus 3 afterward, if I just write plus 3, it's going to be stuck up in the exponent. So to get down, just go 1 to the right, and we're out of it. Okay, alternatively, if you don't want to use the caret, because squared is such a common one, if you look right kitty corner from 7, I see this button that says x squared. It just gives me a square on whatever's right before it. Don't have to worry about moving down. Either option works. Okay, when we go to graph this function, I always hit enter to go into it, and we're going to graph it. And I need you guys to speak up right away if your graph for x squared looks different than mine. Your calculator's frozen. Weird. Let me get you a different one. I'm going to let this one restart. If it does it again, Carson, I will switch out your calculator. But my gut feeling is that that one, weird, there's all sorts of crazy stuff in this one, that one just had a button pressed down, and now it's confused about what it's doing. So there's yours. Does your graph look exactly like mine? Yeah. Pretty close. Do our axes look the same? Okay. So in the case that you have something crazy looking and you need to change your screen, up in the very middle top, what's that button say on your calculator? Zoom. If we hit this, it gives me a whole bunch of options. When we have like menus like this in our calculator, you can do one of two things. You can either click down until you select the one that you want, or you can just hit the number. Now, most of the time, standard will work for us, at least in the beginning, but eventually we'll use a different one. But just in case, I'm going to go zoom, and I'm going to hit 6 to get standard. This gives me -10 to 10 on both axes. So that's like the regular standard graphing scale that we would use. Okay, so do we all agree that we have a function on our graph right now? Something where it only hits once, there's no more than one input, that vertical line thing that we've been doing, it works. Okay, so we're going to bounce back and forth between these screens. As we're looking at functions, it turns out that if we consider the most basic function of any type, and this is going to be a little follow-up definition, we have what we call our parent function. Now, the parent function, really easy to kind of pick out once we get a little feel for it. They are the most basic type of any function. So we'll go ahead and say the most basic type. The most basic type of, and I'm going to say a particular function or a particular type. I'm going to say particular function, and we'll clarify that. Okay, the most basic type of a particular function. Now, at the end of class yesterday, I showed us the graphs at the end of the section, and I mentioned it like, hey, this is good for review. I didn't make you guys take time to write them down, but we only have a few really basic kinds that I care about for us today. So we're just going to get a small little list of these, and we're going to think about them. If I have linear functions, and I'm going to have linear, I'm going to have quadratic, and we'll probably sneak in one more. At the end of geometry, did you guys graph sines and cosines? With waves and stuff? Okay, so we won't use that one then, disregard. We'll use square root as well. Now, these ones, we will all, we'll dig into these together, and I don't expect that you're going to remember everything about these. But a linear function is just a straight line. Can anybody tell me what the most basic equation for a straight line might be? So mx plus b is like the nice version, and everybody I assume at least remembers, or that rings a bell, mx plus b. Now, what's the easiest m value you could have? 1. What's the easiest b value that you could have? 0. So if we use that idea, do you guys agree that y equals 1x is like the most simple of that type? That is our parent function. We have f of x, and you could say y, but I'm going to use f of x. It equals just x. Now, we'll get small little sketches of these down below if you want them. I'll certainly include them. It's up to you. A quadratic function also is sometimes called a squaring function. Now, if you are really good at remembering stuff from 2 years ago, you might remember ax squared plus bx plus c. That's a really common way we talk about these. Well, what's the easiest function that has an x squared in it they might use? Like, I'm going to write one up here in pink, and you guys just tell me, don't write this one down, but tell me if you can make this simpler. Can you make it a quadratic but be simpler than that? If I get rid of 1, is it still a quadratic? If I get rid of the x, is it still a quadratic? Can you get any easier than 1x squared for this type of function? I don't think so. Which means, for our purposes, we would say that the parent for the quadratics is what, Henning? If this one was pretty nice looking, but then we said, hey, it gets simpler when we do this, can you make that have anything simpler than 1x squared? So what do you think the parent function is? Boom, you got it. Okay, x squared. And you can put the 1 in front of it if you want. It's not required. How about the square root? I don't think I've ever graphed square root functions to my knowledge. You might have a little bit. Anybody tell me what you think the simplest square root function is? The square root of x. And it doesn't get any simpler than that with the square root functions. Now, we could do this forever, right? We could do the cubic functions and the quartic, which is 4th degree, and quintic, which is 5th, and so forth and so on. But we don't need to right now. What I really care about is if we can start to get a feel for what the basic functions look like, then graphing can go so fast, so easy. If we want just really basic graphs of these, and I'm just going to do quadrant, I lied, I'm going to do right in the middle. And I'm going to copy this. It's not going to be perfect. I'm not going to put a scale anywhere on here, but I will copy this, and we'll do this a couple times. Don't like that it shows the vertical bar. I don't know why that copied, but whatever. Okay, what's a linear function? What's its shape going to be? A line. And because it's 1x plus 0 is the version of the mx plus b, this is what our linear function would look like. It'd just be this guy. Nothing crazy about it. I can move it up, down, left, right. I can change the slope. All those things happen, or can happen. What is the most basic x squared look like? And if you don't have it in memory, the good news is it's probably on your screen right now. A parabola, like a U shape, but it doesn't get quite vertical. So we have a parabola. It looks something like this. We'll go ahead and say that's f of x. And if you know it, awesome. And I'm going to help us work it out. Anybody know what the root square root of x looks like as a graph? Okay, so maybe some of us do. But if you don't, we're going to build a table without having to write it down. We're going to think it out. Ian, what's the easiest number, or the smallest number, rather, that you can take a square root of? 4. What's the square root of 4? 2. Can we pick a number whose square roots I know that's smaller than 4? 0. What's the square root of 0? So if I plug in a 0, it gives me a 0, right? What's the next square number? 0 times 0 is 0. What's 1 times 1? 1. So I know that 1 comma 1 is on here. And now we'll kick into Guillen's. Guillen, you said 4, right? If I plug in a 4 for x, what's the square root of that? 2. And then we don't have the space to do it, and I guess I'm not really picking a scale. But what if I went to the next square number? What's the next square one? We go 0, 1, 4. What's the next square? 9. How'd you get that? Yeah, it's just 3 squared. So we would have to go all the way to 9 to get to 3, and it'd be like here. What we see is a shape that starts looking like this. Now, here's the cool thing. For all of these functions, if you can remember or even have a place to reference, like a note card or something, what these functions look like, then every other single graph that we deal with is just going to be the parent function that's been moved one way or another. So we're going to have a little bit of time. I want you guys to play on your calculators for a minute, but I'm going to have us do this as an example, and it's up to you whether you want to write it down, because I will write down the summary stuff, but you probably want to jot down some notes. So I want us to consider, and it's in pink, but not to tell you not to write, it's just if you want to write it. I want us to consider the following. Let's say we have the graph of y equals, and I'm going to try to use the same letters that your book uses. So give me like 2 seconds, because every book uses different ones, and I don't remember what we use here. Okay, so let's consider the graph of y equals a times some function. We'll call it f of, and this is going to get ugly, but I promise it won't stay ugly. We're going to say it's a times f of b times x minus h, all inside of the argument of that function, plus k. Now, does this look awful to you guys? Maybe a little bit. Now, here's the cool thing. With our calculators, over the next like 5 minutes, and I'm going to give you some guidance on this, if we can figure out what a does, what k does, what b and h all do, just by playing around on our calculators, then we would have all of these little changes to the parent functions kind of sorted out. So let's do the first couple pieces together. What letter are we going to look at first there? A, B, H, or K? A? Deal. So for these, and if you haven't been writing it, now I would certainly start. I'll switch to another color that tells me we probably should. Let's look at A. A is for, and I'm going to leave this blank for just a second, and I'll help us word this. But I want to think about how we're actually going to work through this. If the only thing that I'm changing is A, and what's the function that you have in your calculators right now? F of x equals x squared, right? Okay, if I wanted to put the same A in this anywhere, where do you think it would go? Like if I'm trying to make sense of how this works, I'm just multiplying the function by A, right? So I could do that here, but I could also do it here. So what I want you guys to do is on y2 in your calculator, not y1, keep the y1 as x squared, but I want you at y2 on your calculators, you're just going to put some number in front of that x squared. And I want you guys, with your groups, pick a variety of different numbers. I wouldn't graph like 30 of them. I would only ever have 2 up. And for example, just to make sure we are all doing the same thing, if I have y equals x squared, what number do you want me to use here? You said 5? Sure. If I do 5x squared, How do you think this is going to impact my graph? Is it going to move it left or right, up or down, thinner or thicker? Check your graph, and I'll be right back because there's somebody at the door. I think you're late.
Okay, Chris was leaving.
Oh, okay. She won't.
No, she's not canceled. She's rescheduled, so I have to leave again later.
Oh, okay. What did this do? How did it change your graph? So I heard it made it little. Is that what you said, honey? There's two of them. So when we graph it, it'll do it in order. The first one up is x squared. There's 5x squared. How did it change it? So give me some words. And every time, I don't know why prime, it's just because of the way that we're like near each other. What was your word? It got thinner. Do you guys agree with that? What if you change a to something else other than 5? Like, can you make it wider? So the challenge right now is what value of a will make this wider? 5 made it thinner. Okay, we'll keep that mental note. What's another number we could use? -4? Oops, we'll go to the original one. Okay, so if I do -4, let's see, does that make it wider? And I'm all goofed up here. X squared and -4. What does -4 do? Oh my gosh. -4x squared. It did what? Holy cow, my calculator's going crazy. All right, there we are. Go to. What are the error with my syntax? All right. If you can't tell, I'm stuck in the exponent up here, which is my problem right now. So I'm just going to clear that whole line, and we'll clear that. And I'll type my x squared back in. If we do a -4, there's my original x squared. What's -4 do? It flipped it. Anything else? It's also got thinner. Okay. With your neighbors, try a variety of numbers and see if we can come up with a rule for how the choice of A impacts our graph. I'm going to give us about 60 seconds. Try different numbers. I'd like to hear you guys chatting. If you're not with a neighbor, you can move for now for this process. You can stand up and you work. Like, we could do a big group of 8 if you wanted to. But about 60 seconds, we'll be back. I want to figure out what does A change. Okay, so give me some examples here, and I'm just going to jot them down as little notes here. If I pick 5, it got wider. When we picked -4, it got, oh, I'm sorry. When we picked 5, it got thinner, right? Thin. What about -4? Thin and what? Upside down. Can you make that a mathy sound? It reflected over something. It reflected over the x-axis. Okay, so if we make it a number bigger than something, it gets thinner. What's that magic number? Like, if I pick 2, is it wider than the original? If I pick 1.5, is it wider than the original? Where's that magic point where it's not wider than the original? Ooh, careful. So I heard 0 and I heard less than 1, and I like both those answers. For this, we're going to go back to here where I left this blank. And I'm going to make some stupid things that I used to remember this. When I think about A, I always think that, oh, that's for orientation, which is a stupid thing that I used to remember. Orientation, to really stress that A. And shape. Now, you don't have to use the capitals and stuff like I do. That's just my dumb device that I used to remember it. When I mean orientation, we're talking about, does it open up like a smile or down like a frown? So we'll make a few comments about this. So 2 little observations that we have. If A is negative, which, how's the mathy way to write A as negative without having to use all them big letters? Less than something. If it's less than 0, reflect where? Over x-axis. Okay. Now, in contrast with that, we have 2 more observations to make. And this one, because I don't want to have to worry about saying it reflects every time, if I only want to worry about how big that number is, like we saw that 5 and -4 both made it thinner. So I don't really care about the negative. That's the reflecting part. We have it covered. If I only want to deal with what the actual value does, we'll talk about the absolute value. If the absolute value of A is greater than 1, what happened to our graph? It got thinner. Now, when we talk about this thing getting thinner, which it certainly does, we can word this a different way. We can say that instead, we have a vertical stretch. So we have a vertical stretch. Now, for this, when we're talking about them, they can be like impossible to identify 100% of the time, and I'll get up on the table and I'll show you guys why here in a minute. But if we're looking at this, we get it vertically stretched, and I lied. Sophia, I'm going to make you turn around real quick. If I'm holding, like if I'm standing on a parabola and my feet are right at the bottom, like right at the origin, and I grab the sides of that parabola, and it wasn't allowed to stretch, it just had to adjust to it, and I pulled straight up, it would naturally have to get thinner, right? That's what's happening when we do that big A value. What if I was holding it, if I'm bigger than 1, that's a stretch, it pulls it upward. What if it was less than 1? Not negative, but between 0 and 1. Instead of pulling up, what would I do? I'd push down, and if I pushed down and it couldn't like bend or like stretch, it would naturally have to get wider on me, right? So when we see this, we see vertical stretch if it gets bigger like that. Now, this thing, just so that we have it like nice, easy language, we'll say thinner. What if, however, we pick a value of A, and the absolute value is between 0 and 1? Instead of stretch, and there's going to be a bunch of answers, we would do the opposite. Instead of pulling up, we go downward. So instead of a stretch, what might we call that? What's the opposite of stretching? Ooh, good. Yeah, I would say compress. So if we have a value of A that's between 0 and 1, then we have a vertical compression. I'm just going to say I will write compression. And instead of thinner, our graph would get wider. Now, the thinner and wider works really nice when we talk about parabolas. With that in mind, I'm going to go to Desmos just because it's a little bit faster than going just keeping it there. But I want to see what this looks like when it's not something that's as straightforward as a parabola that is very clearly thinner or wider. So if I wanted a cubic function, what is the most basic cubic function that we could have? Too many answers at once. If I wanted something cubed, what's the most simple function of that type? X cubed. So there's the parent of the cubics. If I put a number in front of this, like a 2, do you think it's going to get wider or thinner? If I put a 2 in, it should get thinner. Now, because we don't have a distance right between them, wider and thinner is a weird thing to talk about sometimes. But do you agree that the blue one is more compacted towards the middle of it than the other one? So that's what we consider thinner, even if it's not like obviously there. What if we did something like the square root of x? If I put a 2 in front of it, it should get wider or thinner. It should get thinner, and this is a weird one. This one, it's kind of hard to think about whether or not it's wider or thinner. Does it look like it's been, if we use that vertical stretch language, does it look like it grabbed it and just pulled up? It's gotten taller faster. That's what we can think of as thinner here. That's why we use that vertical stretch or compress. It works in every context. Okay, well, we got the first one. A changes the orientation and shape, but we have some more to deal with. Okay, this next few, I think x squared is an easy one to play around with. I want you guys, I'm going to give you like 10 minutes right now. And if you have a computer and you'd rather use Desmos, I'm totally cool with it. But I think it's good practice for the calculators. I want you guys to, you'll jot some little notes down. We'll formalize this tomorrow. We also need to figure out what happens with B. We need to figure out what happens with H. And we need to figure out what happens with K. Now, in your notes, I would do this off on the side because we'll formalize these. I'm going to write them all here so we can see them. And you guys are just going to help me as a basic example. If all I wanted to change was B, I don't have to mess with A anymore. So if we had f of x equals, instead of just 1x squared, what do you think I might put in for B? So 0 is the one thing that I wouldn't want to put in because that would just, it would destroy everything because anything that I multiply by makes it 0. But what if I did like, oh, sorry, f of bx rather, sorry, my bad, bx. Means that anywhere that there was an x, it now gets a bx. I want you to pick a variety of values of b and tell me how this changes my graph. We're going to do the same thing for h, where if we have only the part with h, and I'll work these out for you. I'll get the kind of template started. For the h's, we are only dealing with where that x or the h is. It's in that x minus h. So whatever you plug in for h, it's going to look like this when we do it. And you're going to pick the values of h. The parentheses super matter, just so you're aware. And lastly, for k, we're going to do f of x plus k, which is just going to be on your calculator, x squared plus k. I'm going to give you guys a few minutes. Play around on your calculators. I would go through just each one of these individually. I would say, okay, how does b change on my calculator? Like, as I put it in parentheses here and I pick different numbers, what does it change about my graph? What does h change? What does k change? I'm going to give you guys like 5 minutes. Try various things. If you need to stand up and talk with people, I'm cool with it. You need to get up and move somehow, like I do. Cool. I'm going to pause the video. If you want to move, yeah, for B, I would pick a variety of them. Yep, just like we did on the A when we did it and then we changed it. I would try several of those. Let's see if, before you leave today, if we can have like a basic idea of what happens with these. I'm cool with that. We won't have time for homework tonight. Sorry. But if we jump in right here, we should have a lot of time tomorrow in class, as long as we can get these generalized a little bit today.